6.2, similar polygons. So we're going to take what we talked about in the first section, proportions, and apply them to polygons. So we have a polygon. The definition of similar polygons is a closed figure, which is a polygon, with the same shape but varies in size. So our little symbol is just that squiggly line. So if you think back to the symbol congruent, it's just the top part. It's similar in that it's the same shape but a different size. So what you're going to do is, on this next page, is you're going to take a look at the different figures. You're going to see whether or not they're similar to each other. And then they want you to justify your answer. Okay, so you guys can pause this, look at these two triangles in the first one, and the two triangles in part B, and see if they're similar or not. Alright, so when I looked at part A, I saw that I had two isosceles triangles. So they are similar in some cases because they're an isosceles triangle. But then I looked closely and I saw that their vertex angles were different. So because the vertex angles are different, they are not going to be similar polygons. For this next one, what I did is I looked at the triangles themselves, looked at the angles. Okay, the 80s were the same, and then the 60, the A, corresponds to R. Those would both be 60 because 60 and 40 add up to the 100 that's left over in each of the triangles. I'm just thinking there's 180 degrees in a triangle. I then looked and compared all of the other ratios. So what I did is I went through and I said, well, 6 corresponds to 8, so I went smaller to larger triangle. So 6 over 8 is 3 over 4. I then looked at my I then looked at 5.25, which is the side of the triangle, over 7. Reduced it down, okay, and found that it's 3/4. Did the same thing with the last pair of sides. Because they all have the same ratio, that means that these two figures are going to be similar, okay, just same shape, different size. Alright, we've got three more examples to go through. Right. The next one we're going to be talking about an architect. So why don't you just take a look, read through the next definition in that example, and you can pause now. Alright, so we're going to talk about scale factors. Scale factors are created by lengths of similar figures seen in scale drawings, usually represented by numerical ratios. So it says here that I have an architect prepared a 12-inch model of a skyscraper to look like a 1,100-foot building. What is the scale factor of the model compared to the building? Now, the thing is, I want to keep this, if it's in the ratio, I want them to have the same unit of measure. So I'm going to take and say that my 12 inches is really 1, okay, because it's 1 foot. So I'm going to say it's 1 to 1,100. Right. I could also write it 1,100. Right. I did it this way so that way they had their common units of measure. Okay. So take a look at, you might as well pause the video right now. Take a look at the next two examples, example 3 and example 4, and then when you unpause, I'll go through those two. Alright. So example 3. You have to choose to show, alright, what y equals and what x equals and uv. So the first thing that they want us to do in part A is write a similarity statement. So similarity statement is kind of like a congruent statement. It's just labeling that these two pentagons in this case are similar to each other. So see how I started with the larger one, BCDEA. Because B corresponds to S in the smaller of the two pentagons, I start with S with the remainder of my similarity statement. So now I'm going to look to see, alright, what's my ratio? So 6 to 4 is my ratio, so that's 2/3. So I set up a proportion this way. I said 2 to 3, okay, so smaller to bigger, is equal to y plus 1 over 8. I cross multiplied, right, and you guys can see my steps here. I got 2 times 8, which is 16, equals 3y plus 3. subtracted 3 from each side, I got 13 equals 3y. So y equals 13 over 3. I did the same thing with x, still using my 2/3 ratio. I then took 3 and x, put that on my other side of my ratio. So now I went 3 times 3, which is 9. 2 times x is 2x. Divide each side, so x equals 9/2 or 4.5. They ask us to find out what UV is equal to, and always look back at what they want you to find out, because they'll most likely want you to figure out the length of one of the sides. So what we have to do with this y, 13 over 3, is add another 1 to it. So 1 is also written as 3 over 3, so I add 3 over 3 to 13 over 3 and get 16 over 3. They ask in part B, find the scale factor of the polygon. Well, we did that earlier when we were setting up our proportions. We had 6 to 4, larger to smaller, smaller to larger, either way. When we did it, in this case they want us to do large to small, so we're going to say 6 over 4 equals 3 over 2. The last example gives us 2 different rectangles, and they say we have a scale factor of 1.5, okay, or 5/2. If the length and width of PQRS are 10 by 4 respectively, what is the length and the width of the rectangle WXYZ? So here I set up my 2. I have 15 and 6 were what WXYZ are going to be equal to, so my length and my width. Here's my 10 to 4. So I'm using that ratio, okay, so I've got this 1.5, right, which is 3 over 2, not what I said earlier. So you got 3 over 2 equals x over 4, so I'm finding the 6 here. You cross multiply and find that. Then you do the same thing with finding your 15, which is your length. You could also take your 1.5 and multiply it by 10, you get 15. Take your 4 and multiply it by 1.5. That concludes 6.2.